I'm Alex Reinking from Yale University, and I'll be presenting some joint work with users of this cache on our type-directed approach to comparing ill-typed expressions. So let me walk you through the motivation for this line of work a little bit. Here is an example that we pulled from Stack Overflow, where a novice programmer is trying to split the digits of a random number into 3 separate variables using the Java API scanner. But unfortunately, the code that she wrote is wrong because no constructor for the scanner actually accepts just a plain integer. So one possible repair for this case would just be to parse the integer into a string, which then would allow the programmer to compile their code and continue debugging and interacting and actually interacting. So our goal is to be able to repair these types of errors interactively, reliably, and with little to no interaction or intervention from the programmer. So it's actually useful for experienced programmers too, because these types of errors occur frequently during complicated refactoring actions or during a major version update to an API, things like that. So in order to actually get to that point, the first thing we need to do is solve a simpler problem, namely expression synthesis. And this problem basically just requires that we take a list of all the visible declarations along with the type and attempt to produce an instance of that type if one exists. So obviously, we have to produce a well-typed statement as a result, but it should also be useful. So to do that, we deploy a system with process that helps us decide whether or not an expression is good, depending on how often it uses local declarations and how many we use data. So the way that search actually works is via this synthesis graph data structure that I pictured up on the slide here. The synthesis graph sort of models the idea that types are constructed from functions, and functions are in turn satisfied by the types. Here on the slide, you can actually see that in orange we have a function node for a new buffer reader constructor, and incoming to the buffer reader is the type node for just the buffer reader. But then from that function, we have 2 arrows outgoing to the reader and int type nodes, because those are the 2 parameters those are the 2 types of parameters that the buffer reader requires. Cool. So to actually go ahead and compare an expression, what we do is we view the broken expression as a parse tree, and we start from the leaves and replace any bad expressions with newly synthesized repairs of that type. Along the way, we add the good sub-expressions into the synthesis graph at a low cost, so that the resulting expression closely mirrors that of the original expression. So how well does the algorithm work? We built 2 implementations to test these ideas. The first is an IntelliJ IDEA plugin that offers synthesis results as a code completion helper. So a user can just call our tool and declare a variable we're trying to satisfy a parameter for the function call and get a list of suggestions. And we also implemented it as a compiler extension to the standard Oracle Java C compiler, which will initiate a repair whenever it encounters an ill-typed expression. We evaluated our synthesis engine against 50 benchmarks that were taken from previous related work. And the way that these benchmarks work was by removing a line of code program, calling our engine, and seeing whether or not we recovered the original line of code. In all 50 benchmarks, we managed to recover the original line of code. And in 31 of the 50 benchmarks, we managed to actually rank that line of code first. The median time for synthesis was about 30 milliseconds, which is more than fast enough for interactive use. And if you're interested in learning more about the algorithm, folks are outside, so hope to see you around, and thank you for listening.
So we had some great talks on this session, and I just want to remind you again, outside and please go there, take further questions, find your works. And now we'll move on